Hey, it's Horner. Hey, AP Physics C. So this is rolling without slipping. Anytime you have a ball going along a incline or along the floor, as long as there's enough friction there, it will roll without slipping, and that is static friction and not kinetic friction. If it was kinetic friction, then we would have that slipping part going on. So all the kinetic energy is really just all of the translational, and then all of the rotational. Notice this is for the center of mass of the object. When a body is rolling without slipping, there's another equation that holds true, and we know that that is the velocity of center mass is just equal to the angular velocity times the radius of that object. And so you can combine this equation to make one of two. This would be if you want the translational energy, and this is if you just want the rotational energy. So let's go ahead and take a look at this very first question. It says I have a solid sphere of mass m and radius r. So there's our solid sphere. It's going down an incline, has a length L, and there is an angle here, theta. And I don't know why. I've tried to figure out why this is happening, where we get this really funky kind of looking thing over here, but I don't know, so I'm not going to worry about it. Just know that it does it, and it's just very irritating. Something that Adobe started. So anyway, here's our sphere. It is a solid sphere. It does have mass m, and it has radius r, and they want us to use conservation of energy to find the linear acceleration and the speed at the bottom of the ramp. So let's go ahead and do that. We're going to say the potential energy at the top plus the original translational kinetic energy. So let's change this to kinetic. So this is plus the original kinetic translational energy plus the original rotational kinetic energy is equal to the final potential plus the final translational kinetic energy plus the final rotational energy. And so now we've got that. Let's cross off things that don't have any value. So at the top of the ramp where it's not moving, those don't have a value. And at the bottom of the ramp, the final potential energy will not matter because we're going to say that this is 0 meters here. And then we're going to say that this is our height, h. But what's interesting is we're not going to use h here. Instead, we're going to say that this is just L times the sine of the angle. So this is our length, and then this is L sine of the angle. And that will make everything come out a little bit better. So we're going to start with mgh. We're going to add to that 0 plus 0, and then we've got 0 here, and we've got our 1/2 mv squared plus 1/2 I omega squared. Next thing we'll do is let's do some substitutions. So this mgl sine of the angle is equal to 1/2 mv squared plus 1/2 of I omega squared. Then we're going to say mgl sine of the angle is equal to 1/2 mv squared plus, now we have 1/2, and then I for a solid sphere is 2/5 mr squared. And we're going to multiply that times, now because we want this to be the linear acceleration or the translational acceleration and the speed at the bottom of the ramp in a straight line, we're going to go ahead and we're going to say that omega is equal to v over r because we know that v is equal to omega times r. And so here we're going to have v, but notice this is squared, so I got to square that and square the thing on the bottom. Best thing about this problem is your mass cancels out all the way across, and then your r squared cancels out, and you're left with gl sine of the angle is equal to 1/2 v squared plus 1/2 times 2/5, and so that will give us 2/10 or 1/5 v squared. Next thing we need to do is combine these two things. So we're going to have gl sine of the angle is equal to, this is going to be 5 over 10 v squared plus 2 over 10 v squared, and that will give us 7/10. So this is GL sine of the angle is equal to 7 over 10 v squared. Now that we've done that, let's just go ahead and solve for v. And so here v is equal to the square root of 10 times GL sine of the angle, this is all under the square root, all over 7. So that is our velocity at the bottom of the ramp. Now that we've done that, I think what I'll do is I'm going to change color here if I can. So I'm going to go to, whoops, changed everything, which is another problem with this. So let's go here, put a couple dots, maybe do this, and go back and try to change colors again. Oh well, we tried. It's the best we can do. So let's now say we know that VF squared is equal to VO squared plus 2 times the linear acceleration times the change in position. So we have our equation for our final velocity, or our speed at the bottom of the ramp. We also want to find out what is A, so this is what we're going to try to solve for. Final speed is just really simple here. It's VF squared. Here's VF. We're going to square it, and so that will give us 10 GL sine of the angle all over 7. That's going to be equal to, this thing is 0 because at the top we don't have any speed, and then it's 2 times A, and then our change here in height is going to be, 2A delta X, and that's actually along the ramp. And so that's going to be L for our length, because you do go all the way across there. If we rearrange this for A, we're going to get A is equal to 10 GL sine of the angle all over, and then we get 7 times 2 times L. Notice that this is an L here, so we got to be careful. Notice that the L's cross off, so those are gone. 10 here and 2 reduces the 10 to 5, and so now our final equation is A is equal to 5 times G times sine of the angle all over 7. And so that is our final equation. Next thing they want us to do is do the same problem, but this time they want us to use rotational dynamics. So I'm glad that that came up with that line there. That should help out a bunch. Same thing again, we've got our sphere. We do have a line going down. This has mass m, and it has a radius from here over r. We have L again, and we also have our angle theta. Okay, so this is totally different. They want us to use dynamics, so the first thing we need to do is create a free body diagram. So for that free body diagram, let's go ahead and make a ramp. So let's just go ahead and make it solid. We're going to put a dot for the actual object, and then we're going to draw all of our vectors here for our free body diagram. So this is going to be mg. We know that going up at this angle is going to be Fn. We know going in this direction is the force of static friction, which allows it to rotate. So now we're going to do components. We've got one component there and another one there. This angle is theta, just like this one. So we can even put that angle in over here. This side is going to be mg, cosine of the angle. This one's going to be mg sine of the angle. So now we've got everything we need. We also are going to say this is positive y, and because the ball is going down the ramp, we're going to make this positive x. Let's start with some of the forces in the x direction are equal to mass times acceleration in the x direction. The thing going down the hill that's positive here is mg sine of the angle. Going in the opposite direction is the force of friction, and that's equal to the mass times the acceleration of the system in the x direction. We'll rearrange it for the force of friction. and that's equal to mg sine of the angle minus the mass times the acceleration in the x direction. So now that we've done that, let's go ahead and think about torque. So the sum of the torque should be equal to the moment of inertia of the solid sphere times the angular acceleration. So for this, we have a radius. We also have a force, and that force, remember, is the force of friction. So that's the force that we're really worried about, and that's the one that creates the torque. Without that, the ball would not roll. So our force here is the force of friction, and we're going to multiply that times the radius of the sphere, and that will be equal to, remember, this is 2/5 times mr squared, and then we're going to take that times alpha. The other thing that we need to do is we want the linear acceleration. So here we know that alpha is equal to the linear acceleration over r, and so we're going to plug that in. So here we go. ff times r is equal to 2/5, and then this is going to be mr squared times a over r. At this point, we're going to get rid of one of the r's, and we're left with the equation ff times r is equal to 2/5 times m times r times a. Now we can rearrange the equation for a, and a here, sorry, we're not going to rearrange it for a, we're going to rearrange it for ff so we can set the two equations equal to each other. So let's just get rid of the a here. We know that ff is equal to 2 times m times r times a over 5, and then that is times r. Our r's will cancel out, and our force of friction then will be equal to 2/5 times m times a. Okay, so we have force of friction here, we have force of friction from torque, and we're going to set those two things equal to each other. So here we go. We have 2/5 times m times a, and that's equal to mg sine of the angle minus ma. We can get rid of the m's all the way across, so those are gone. Now we have 2/5 of a is equal to g times the sine of the angle minus a. We need to add a to both sides, so we're going to do 5 over 5a plus 2 over 5a, and that gives us 7 over 5a, and that's equal to g sine of the angle, and guess what? We get a is equal to 5 times g times the sine of the angle all over 7. If we go back to the previous problem, you see that we get the same thing. A is equal to 5g sine of the angle all over 7. Since that holds true, let's solve for the final velocity of the ball at the bottom. And so this is equal to VO squared plus 2 times acceleration times the change in position, which we know is L times the sine of the angle. So here we go. We're going to do VF is equal to VO is 0, so we're going to do the square root of, because we have to take square root of both sides, this will be 2 times, now our acceleration is 5 times g times sine of the angle times, and then our change in position here we said was L, because it's that length there. And then we're going to divide that by 7, and that gives us the square root of 10 times g times L times the sine of the angle all over our good friend 7. And you'll see that the final velocity here and the final velocity from using energy is the same, 10 GL sine of the angle over 7, and take the square root of that. Same thing here. So kind of a neat, interesting thing that happens when you go through and solve this using either dynamics or energy. You do get exactly the same answer, which is cool. Now we have a hollow sphere, mass of 1.5 kilograms, radius of 2, rolls without slipping down a ramp at 33 degrees. After it suffers a drop of 1 meter in vertical height, what is its translational speed? So we're going to do that first, and then we're going to see what its angular speed is. Okay, so here we go. Let's go ahead and draw a picture of this. So I think what we'll do is we'll just kind of do that so that it does that there. And now we've got our hollow sphere, and we know that we have an angle here of 33 degrees. This one has a mass equal to 1.5 kilograms, and we know that our radius is 2 meters. Pretty big ball. We know that the distance, or the change in height here, is 1 meter. So here h is equal to 1 meter. Alrighty, so let's actually do both on this one slide. So we're going to do translational, and then over here we can do the rotational. Translational, we're going to use conservation of energy. I think that's probably the easier way, the two ways to do it. We know the original potential energy plus the original translational plus the original rotational is equal to the final energy potential plus the translational kinetic plus the rotational kinetic energy. These are 0 at the top, and that one is 0 at the bottom, so those all go away. So we're basically doing what we did before. mgh is equal to 1/2 mv squared plus 1/2 I omega squared. The m's will cross off here in just a second. We're going to do mgh is equal to 1/2 mv squared plus 1/2, and then the I value for a hollow sphere is 2/3 mr squared. So this is 2/3 mr squared, and then we need to take that times omega squared, but we said earlier that we're doing this linear, so this is going to be v squared over r squared. And where did that come from? Remember, omega is equal to v over r because v is equal to the angular times the radius. Alright, so we've substituted that in. We can go ahead and do some of our math. We can also get rid of the mass, so mass won't matter. This is GH. That looks like an L, so let's make it an H. GH is equal to 1/2 v squared plus, and then 2 over 6 is 1 over 3. The r squareds go away, and this will be v squared. So now I have GH is equal to 5 over 6, because we just do a common denominator of 6 and then add them, so that'd be v squared. So our v for this hollow sphere is now going to be 6gh all over 5. So we've done it for the translational. On the next slide they want you to do it for rotational, so we're going to go ahead and do it here. So I'm going to just put rotational velocity. Remember, we did say v is equal to omega times r, so we've got mgh is equal to 1/2 of the mass, and then instead of v we're going to put omega times r squared. So we're basically just using this same equation, but we are substituting in for the rotational energy, plus, and then we've got 1/2 of, we said that the rotational inertia is 2/3 mr squared, and then we want omega squared here. Masses will cross off all the way across, and so we're left with GH is equal to 1/2 of omega r squared, that quantity squared, plus 2 times 1 is 2, 3 times 2 is 6, so that would be 2/6 r squared times omega squared. So obviously we can add these two together now, and so we have GH is equal to, common denominator is going to be 6, so this will be 3/6 omega squared r squared plus 2/6 omega squared r squared, and so we're going to end up with GH is equal to 5 over 6 omega squared r squared. At this point we need to solve for omega, And so omega is going to be equal to the square root, so of 6gh, so this is 6gh over 5, so the 5 is going to be on the bottom, and then we have to divide that by r. And you'll notice that's interesting because over here we have 6gh over 5, the square root of that, but we don't have r on the bottom because this is translational, and to get the rotational we just divide by r. So you really don't have to do all this unless you're asked to prove it. So this equation and this equation are related in the fact that we just needed to take the translational and divide by r, and that's what we did, and that's what you'll see. And that is the end of this set of notes.